With the preparation of these parallel prefix sums and compacting of subsequences, we can finally come back to sorting. So how on earth would compacting sequences, subsequences, help in sorting? It helps to parallelize Quicksort. But let's start very basic. You've seen Quicksort in one of the previous times. It essentially, well, it was a divide and conquer algorithm, so it does something and then it recurses. And it recurses on two parts, left and right. And these two recursive calls are not at all depending on each other. They work on disjoint areas in the array. And Quicksort is particularly nice in that it doesn't even have to do anything once you return from the recursive call. So we can definitely take Quicksort and just say, call the left and right recursive call in parallel. And that's what we'll do. But this is not enough. If we were to do only that, if we were only to recurse, to be parallel on the recursive calls, we would still have the first partitioning step, and that takes linear time because it walks sequentially through the list. So the best we could hope for if we would only go for recursive calls in parallel would be reducing the time from n log n to n, right? Then we're already dominated by the first step. If we want to do anything more fancy than that, we have to also parallelize the partitioning itself. And for sure, the code that I showed you has the same issue that the sequential prefix sum code had. Everything you do seems to depend on what you just did and how the comparisons turned out. So how should you parallelize this? So you have to look at the problem from a different perspective again. And the solution here is to decouple different steps that the partitioning code I showed you does in a twisted and merged way. So you might not even think about them as separate. But you can split partitioning into these three things. You first determine for every element whether it's smaller or larger than the pivot element you've chosen. And then you take the subsequences of small and large elements. The only thing that we have to do is get them separate, all the small ones to the left, all the big ones to the right. And that happens to be exactly the compacting subsequences problem, right? The elements that are smaller than the pivot initially can be an arbitrary subsequence of your array. What you want is take them all and put them in a contiguous part at the beginning. And to make this work, we use a bit vector where we store the outcome of the comparison, whether an element is small or large. I think I have detailed code for this, but before we do that, let's see a very small example on that again. So I'm making up some input. Oh, humans are terrible at random number generators. But let's still do this one. Let's suppose we use the element 5. Okay, I think the code I had was to take the last element as a pivot, so let's make it the last. Number 5 is our pivot element, which also means that we don't have to partition the 5 itself. That's out of the game. What remains to be done is the other elements should be separated into small and large. So step 1 is find this bit vector, which is 1 if the element is small and 0 if it's large. Maybe we should call it small then. Okay, so we compare. 3 is smaller than 5, so I should put in a 1. Okay, we can do this. And while we're doing it, let's do the same for large. But that one's simple. I just negate everything. I don't need to think at all. Now we have two subsequences defined. Did I screw it up? No. Two subsequences given by the 1 positions. And now we have to take them and compact them. So we take our input array, and the first one, and well, how can I draw this? We compact the 3 and 2 and 1 and 4 into the left part, and we also compact the large elements, and we add the offset so that we leave room for the pivot and the small elements. So here the pivot should go, and then the large elements, there's just 7, 8, and 9. Conceptually clear how this works. So then the code shouldn't be very confusing once you get to the details. There's a lot of code. I don't know, I didn't find a more concise way to write it. But it also has the recursive part. So let's briefly walk through this. That part is like in the sequential Quicksort. You choose some pivot element, and then you call the partitioning procedure. And we need for the recursive call that the partitioning procedure returns the position where the pivot landed. If we have this, that defines us a left and a right subproblem, and we recurse in parallel. So I'll just write in parallel and then do two things. That's my notation for doing it. Again, we take the most abstract point of view. Please, operating system, do your magic and execute it in the best way possible. The parallel partitioning is the more interesting part. We make sure that the pivot is the last element. And then in parallel, we compute these bit vectors S and L. That's the first stage. OK, this notation is maybe something. I'm not sure I use it anywhere else in the course. So I'll write, if you have some condition and you put square brackets around it, that means it's 1 if that condition's true and 0 otherwise. It's maybe not so important, but it's useful, so I think it's a good notation. So we compute the small and large bit vectors, just as I did in the example. We do that in parallel, so this again runs in constant parallel time. Then we compute the parallel prefix sums of those bit vectors, because that's what we do for compacting. And the last step is to, in parallel again, every processor has a single element that he's in charge of, he or she is in charge of, and that this processor writes to the correct position. Are there female processors? Well, whatever. So that's the step here. Depending on whether it's a small or large element, it goes to the left or right part. And you can check whether I made mistakes in the indices. But this is how it should look like. Questions on parallel quicksort? OK, then let's see how well it does. I'm looking here at the first line. We're looking at the time first, the parallel time for one partitioning step. And it says everything in the code is constant parallel time, except for, again, the call to our parallel prefix sums. And if you check, everything that happens is either a parallel for loop with constant amount of work inside, or it's again just a simple instruction. So the parallel prefix sums dominate the parallel time. That's for one partitioning step. So well, it says partition here, so I don't have to write it again. One partitioning step is logarithmic time. But the whole sorting does a whole bunch of those partitioning steps. And for the parallel time, you have to look at how many of them you cannot do in parallel. And that's the ones where, well, the next recursive call depends certainly on the outcome of the current partition one. So the depth of the recursion tree is the limit to how much you can parallelize the partitioning steps. I can do in parallel all the recursive calls on the same level, the left and right, but I have to wait for either of them to start that the parent partitioning round is finished. Okay, very quick picture on this. So the parent might split this in here. Then the next part, so this is one node in the recursion tree. The next one might split it like this. And whenever I draw these little edges, this is actually I have to wait for my parent to finish before I can go to the next step, whereas anything that's on the same level can run in parallel in principle. Well, this goes on until you have only singleton elements left. I'm reluctant to continue drawing. But the height of the tree will be the longest chain of things that depend on each other. So if we multiply the height with the parallel time of one partitioning step, that gives us an upper bound for the total parallel time. Okay, the height of the recursion tree is only logarithmic in expectation because it's choosing random pivots. So the only thing we can guarantee here is expected log squared parallel time. But let's also look at the work, because remember, if we have work in time, we can compute what we would need as time on any machine with fewer than n processors. So work is also important. The partition is actually linear if you don't look at the prefix sums. And if you use the fancy prefix sum algorithm with the blocks, then we can get this to linear time as well. And that means, well, this log squared is again using the simple prefix sum algorithm that has n log n work. If we use the work efficient prefix sum, then the whole parallel quicksort is work efficient. It has n log n work, which is, well, the same as a sequential algorithm for sorting. At least if you're not sorting integers, right? Okay. So to reiterate, Quicksort is work efficient, and it has log squared expected time in parallel. Okay. We can also parallelize Mergesort, and that will be the main contender again. I promise we'll do a quick break after this. I know this was fairly tough stuff compared to the other sessions, so it was a bit dense. So take a deep breath, and let's look at Mergesort. It's same as for Quicksort. It's a divide and conquer method, so it does recursive calls, and we can do the left and right child recursive calls in parallel. That's easy, but it won't get us below order n. So we again have to think about the combine step and how to do that in parallel. Now it turns out for Mergesort, this is actually a tiny bit trickier than for Quicksort, I think. That's why I present them this way. Because, well, remember how merging works. The sequential merging worked by iteratively going through the two sorted runs and always taking the smaller of the two and putting them in the output. It seems hard to do that in parallel because, again, you need all the previous decisions to know where an element goes to. But we can't do this in parallel. If we want to parallelize this properly, we need something that's independent that can be independently decided for every individual element. And so here's a way to do it. Let me maybe draw a picture first before I explain the concept. You remember my pictures, the sketches from how merging works. Let's suppose we have an element that's right here in the first sorted run. We know exactly how many elements are smaller and bigger in the first sorted run because that's its position. It's sorted. It's bigger than all these and smaller than all those. In the final sorted output, its position is again the number of elements that are smaller than it. The position of an element in the sorted list is its rank, which is the number of elements less or equal to this given element. Okay, we know the rank of any element inside its own run. We have to find the rank of this element inside the other run. Okay? So I have to, oops. Okay, now I'm way back. I have to find where this element X belongs in this run, but it's sorted, so I can use binary search. I can compare X with the middle, and if it's bigger, I can compare X with the 75% thing here. So eventually, I will find that if X was in this run, it would belong to this position, at this position, which means it's smaller than so many elements from the second run. If I add those two numbers up, I will get the rank of X in the sorted list, in the entire list. So that's what's written down here. The number of elements less than X, well, they have to come from somewhere, so they can only be in this run or in this run, and if I add those up, I'm done. One of them is just given by the position of the element in that sorted list. The other we can find with binary search. Okay, I don't put down more details on this. Maybe I should have spelled out the code. But then again, if it's not in the slides, you don't have to know the details. So for each element, you do a binary search of this element in the other run. So that would, again, it would be a loop over all the elements. And, well, there will be two parts, one for the elements from the first run and one for the elements in the second run. You assign each one processor to each element and use that processor to do a binary search in the other run. That gives you a number, the number of elements that are smaller in that run. And you also have your ID, or the position of the element you're responsible for, and you add those two up, and then copy your element to the output at that position. That's how you would do parallel merge. And parallel merge sort uses parallel merge in the same recursive call as we've seen for Quicksort. So let's briefly see how much time that takes. I don't think binary search takes linear time. I would rather have this be log n. That's just a typo. So the merge procedure that I didn't spell out, it only does constant time things in parallel except for the binary searches. The binary search itself, again, seems hard to parallelize, so we don't even try. In this simple case, you just do a sequential binary search, but with all the processors in parallel. So you get logarithmic time, parallel time for the binary search for each element, and the rest is constant. So in total, it's logarithmic parallel time for merge. And for merge sort, same reasoning as for Quicksort. You have to wait for the child recursive calls, well, before you can merge their results. So the height of the tree is again what limits the parallelization of all those merging steps. So you get the same result as order of growth, but this time it's worst case because Mergesort doesn't have to randomize or doesn't have to choose pivots. I mean, if we don't say anything, I assume worst case, but let's be explicit. So the advantage of Mergesort over Quicksort, like in the sequential case actually, is it achieves the same order of growth, but in the worst case, not only in expectation. But let's look at the work. For Mergesort, we have those n binary searches for every element in a single merge. For every element, I have to do a binary search in the other run. That gives me a log n each. So that's n log n work in total for a single merge. And that I would have to add up over the, okay, this analysis would have to really solve the recurrence. But it will come down to an n log squared n. That used to be the work of Quicksort before we plugged in the work efficient prefix sum. Then Quicksort was work efficient, n log n work. Mergesort doesn't get this easily. Okay? It's still possible to do it. That requires more tricks. It's essentially, again, a blocking trick, but I want to spare you with the details. I give some hints in case you're interested, but I don't think I want to discuss it here. And the final slide for sorting is just a few remarks about the state of the art in theory. If you're looking at this type of PRAM model that was our most natural one, concurrent read, exclusive write, you can tweak the sorting methods we've seen to get log n parallel time instead of the log squared. You don't get it in any very direct way. It's still a reasonable method that comes out of it, has potential to be fast in practice, but is a little more complicated than the ones we've seen. That's the theory side. I want to add a little remark on the practical aspects. There's essentially two challenges. One comes from the synchronization. If you think back to the prefix sum algorithm we've seen, it very much relied on the fact that on the PRAM, all reads happened before all the writes, and we didn't have to do anything to guarantee that. That's not true in the thread-based languages that are most widespread. However, there's languages like MATLAB and NumPy libraries for Python that express computations as working on whole arrays or matrices. And to some extent, they also can parallelize things automatically. And there again, it feels much closer to this type of programming we did. So it's not so much a limitation of the theory that we make assumptions that are completely unrealistic. It depends on the programming language you look at. And some get actually fairly close to the type of programs we've seen. They do have some restrictions what you can do in each individual step. It has to be roughly the same thing you do on the arrays. But the type of algorithms we did would work in these frameworks. The second challenge is what's listed here. If you start millions of small jobs, each just a few cycles long, then the overhead for managing them, for scheduling them to the cores, etc., is probably more expensive than the work that they do. So what you would have to do in most actual implementations is group the work into bigger chunks. And you're definitely invited to look into some of these if you're interested how this is done in current programming libraries. I advocate the Java library because I know it. You can look in other ones too. Java has the additional benefit that it's open source, so there's one definitive source for the Java standard library. Their parallel sort uses concepts that we discussed here, but it doesn't go to the fine level of treating every element with one processor. But still, the PRAM models we talked about show the fundamental limits of how much you can parallelize. And that's the main message I think you should take from this unit, or from the whole module on parallelization. There's fundamental limits of how much you can parallelize, and you can get fairly close in actual programming languages if you invest a little engineering work. Okay, that concludes the sorting module.